Welcome to Calculus, Chapter 5, Section 3. And what we're doing is exponential functions that have any base that you want. So what we're doing is we're looking at the derivative of a function that is a to the x power. Now there's sort of a long explanation that you could do with this, and because I don't even have this memorized, so you might be questioning my dedication to calculus when I don't memorize certain things. But what I like to think about is if I just had a function that was y equals a to the x. Well, what you could do is you could natural log both sides. And so when you natural log both sides, you could actually derive this using the chain rule, which is 1 over y dy dx, which we'll talk about more in a future section. And instead of taking the derivative of this, I would just move the x in front, and natural log of a is just a constant. I guess I should have rewritten it first. X natural log of a. Well, since natural log of a is just a constant, and we have x to the first power, the derivative of this is just the constant, natural log of a. So dy dx is equal to, as I multiply y over, well, what is y equal to? Y was originally equal to a to the x power. So what I'm getting at is the derivative. Oh, whoops, I wrote it wrong. Sorry if you've been writing in pen. So the derivative of a to the x is equal to natural log of a times a to the x power. So it's very similar to the rule for e, except we have this natural log in front. Now, if you're questioning me, which is fine, I get it, you could have actually taught the derivative of e the same way, the derivative of e to the x, because it's equal to natural log of e times e to the x. Well, what is the natural log of e? That is equal to 1. So it still works. This rule still works. We might just be at the point, at this juncture, to memorize this rule, and then we can investigate this when we get to what is called implicit differentiation. So right now I'm just going to say you might want to memorize this rule, and then we can move forward. Right, so we could do this problem the same way as we mentioned before. F prime of x, you could do it the same way of natural log of e times e to the cosine of 2x. Oh, whoops, this is supposed to be from the previous. Anyway, we'll put it all together. Times the derivative of cosine is negative sine. You leave 2x alone. Times the 2. And you would get the same answer if you did it with the new rule, because the natural log of e will cancel, or if you did it from the previous units. So we're looking at negative 2 sine of 2x times e to the cosine of 2x of any of those problems. So let's get a little bit fancier. Sorry, if you need to pause, please pause and make sure that you understand what we're talking about. So as we move forward, so this first one is pretty straightforward. Now it is still the chain rule. Chain. So the derivative of this will be natural log of 4 times 4 to the x squared, but then times the derivative of x squared, which is 2x. Now it's completely up to you if you want to rewrite any of these. Some people might just put in parentheses and rearrange the order. Just make sure that you are clear that this is a power to a power. It's sort of interesting. As we look at the next one, this is a product rule. There's a product in there, right there. So that's your clue that when you take the derivative of x squared first, leave 2 to the 2x alone. That's a times, by the way. I should use parentheses instead of that dot. Plus, you leave x squared alone times natural log of 2 times 2 to the 2x. But again, the chain rule, you have to multiply by that 2 that's in front. Now, at this point, I think it would be up to you if you wanted to factor things out. For instance, each one of these has a 2, an x, and a 2 to the 2x. A 2, an x, just one of those x's, and a 2 to the 2x. So you could factor it out if you want. I actually don't have an answer key to this. 1 plus, let's see, we have an x natural log of 2 still there. But either of these options are acceptable. Oh, by the way, you could actually combine the 2's together, multiply with the same base. So what you could do also is rewrite it as x times 2 to the 2x plus 1, and same thing with this one. So that's another option. H of x, I think, is pretty straightforward because there's no product rule, there's no quotient. Well, there is a chain. So the base is 5, so natural log of 5 times 5 to the 2x minus 3 times the derivative of 2x minus 3, which is 2. There you go. You can rewrite that in any order you want now. And let's see, I'll go to purple now. Here's another product rule. So p prime of x, it's going to be the derivative of x, which is 1. You don't have to write it. So 3 to the negative 2x. And then plus, leave x alone. Derivative of 3 to something is natural log of 3 times 3 to the negative 2x times the derivative of negative 2x. And of course, you could factor out a 3 to the negative 2x. This is optional. And then you'd be left with 1. I'd rewrite it as minus 2x natural log of 3. So either of these answers are acceptable. Just throwing in some thetas in here. Not sure if any of this is confusing you. But in this problem, your derivative then would be, again, a product rule. And in here's a chain. So the derivative of 2 to the would be natural log of 2 times 2 to the negative theta times the derivative of negative theta, which would be negative 1, plus leave 2 to the negative theta alone. The derivative of cosine is negative sine. Leave pi theta alone times the derivative of pi theta, which is just pi. Again, you could rewrite this in many different ways, but I'm not going to. Feel free to pause, make sure you understand everything, try to simplify if you'd like. Moving on to the next one, you have a quotient rule now. So the derivative of the top is natural log of 3 times 3 to the 5x times the derivative of 5x. Leave x alone from the denominator, minus the derivative of the bottom, which is 1, you don't have to write it, 3 to the 5x, all over the denominator squared. And you could simplify that further. I'm not going to. This is good enough. And then one more, I think this is it on this slide. No, there's one more down there. Is another quotient rule. The derivative of the top is 2x. Leave the bottom alone. But again, you could combine with multiplying with the same base. Minus derivative of the bottom. Don't forget about the chain rule there. Times the top. All over the denominator squared, which I would write instead of that thing squared, you'd multiply a power to a power. A power to a power is multiplication. So over 6x. Now this is one where you can for sure, let's see, I'm seeing a 2 to the 3x that you could cancel out on top, factor out, excuse me. And I'm seeing just 2x minus natural log of 2 times 3x squared. Notice that I only factor things out when it's obvious. But you don't have to do everything I do. Something like this should be about your answer. So this next problem, a little bit interesting, all right? Because they were asking for the value of x, where the normal line would have a slope of 2. Well, if the normal line has a slope of 2, what does that mean for the tangent line? Well, the tangent line is perpendicular to it, would be a slope of negative 1/2. So if you find the derivative of that, which the derivative would be natural log of 2 times 2 to the negative 3x times negative 3, that needs to equal negative 1/2 now. And at this point, I'd probably just go to my calculator and make sure that I find out a value for that. Another trick with your calculator, because I've not shown you this before, is you can actually double check that your answer is correct. If you go to y equals and you type in that function 2 to the, I forgot what it was, negative 3x, and you can type in your answer. All right, so that what we got for the derivative was natural log of 2. So this is a trick to see if you have the correct derivative, times 2 to the negative 3x power times negative 3. Now, in the previous lesson, I told you how you can use your calculator to find a derivative at a point. You can actually find the derivative at every point. So what I'm going to show you on your graph is you should see a curve and then the graph of the derivative. So you can see how it's decreasing. The blue curve was decreasing everywhere. So that means the red curve needs to be below the x-axis, and it looks like it is. Now if I go to y equals into a new equation, I can actually go to math and find the derivative and hit dx, just like I did in the previous lesson, alpha y1, alpha trace to grab y1. I'm looking at the top equation, and you can actually put where x equals x. And if I did the correct derivative, my black curve will lie directly on top of my red curve. Now it takes the calculator a little thought process, and what you're doing is you can double check that you have the correct derivative, and we do. You don't see the red curve anymore because the black one is directly over it. Now the last thing about this problem, let me hide this because if I keep it there it's going to take a while, is you can actually set the equation equal to negative 1/2. And what I want to see is where my red curve hits my purple curve. So I go to my graph and I can hit second trace. My fifth option there is my point of intersection. Now make sure you grab the right equation. So I'm going to go down to the red equation, go to where the point of intersection is, my purple equation, hit enter again, and my best guess, you get an answer of about 0.685. I'm not sure if you could have done this by hand. Let's see. Let me just try real quick. To get rid of negative 3, you divide by it. You go to cancel that out. So that would go into the denominator. To get rid of natural log of 2, you would divide by it. So that would also go into the denominator. And then to undo 2 to a power, you'd want to do log base 2 of both sides, and then divide by 3. So if you typed into your calculator, it'd be log base 2 of that very ugly thing, 2 times 3 times natural log of 2, all over divide by that exponent negative 3, and you should get the same answer. But I'm running out of time, so I will stop right there. Please pause and double check my math, my arithmetic, and I think I need to come back to finish the last rule for logs.